我就放弃了。
那就
我再注意一下。
Okay. Is it on? Yeah, you me. Good.
It's really small anyway.
Okay.
So sorry for the delay. It's our great pleasure to have Professor Brink to visit Taiwan and the center for this and also he will give a talk this morning on something he has been working recently and actually throughout his I would say throughout his from early on. He's going to tell us about the importance of symmetry. Actually, not just a space-time symmetry, but some global symmetry in supergravity. How it's going to help to define the fundamental theory of string theory. Professor Brink is a distinguished scholar. He's one of the pioneers and inventor of many of the fundamental construction in string theory. For example, the integral force we have been talking about in the ADS-CFT proposal was constructed by him in the 70s. So many of the physicists in the field are either his students or collaborators, and so you see his name all the time. Yeah, so it's really a great honor to have him with us today. So please welcome Professor Brink.
So thank you for that we come here. It's very nice. Is this? I just want to. Yeah. So, okay. Thank you very much for having me here. So I'm going to describe a bit of what I've been doing more recently. You see? So since I'm very old, and I've been working in superstring theory almost from the beginning more or less. And what is interesting is that somehow we always come back to the corners of the theory, in a sense, to the limits of the theory. Namely, field theory limits, like 11-dimensional supergravity, 10-dimensional Yang fields, and the 4-dimensional versions, n equals 8 supergravity and n equals 4 Yang fields. And you might think, that we should have known all about those things and gone to the more, perhaps deeper problems. But even after 40 years, it seems worthwhile to study them. And what I will try to convince you is that I still think that there are things to understand in these theories. So, as field theories, these theories, n equals 8 supergravity and n equals 4 Yang fields, are very complicated theories, but they have very simple results. What I will talk about today is essentially about supergravity. It's been around for 40 years, and n equals 8, that came a bit later than the n equals 1 theory. That was the starting point. And it was done by Clement and Julian. And if you ever get hold of that preprint, which probably is a classic, there's 124 pages. And it's full of formulae. It's a theory which consists of 128 bosons and 128 fermions. And if you go take a field theory course, usually your field theory books that start with having a 5 to the 4 theory, and then you can do renormalizations, and then you have one field, Think about having 256 fields. There are lots of couplings. So, you would think, that a theory like that, if you randomly constructed, it might be a complete mess. However, this theory is not. If you do calculations, you'll find that there are some very simple results. For example, if you look at the 4 graviton 1 loop amplitude, to complete the S-matrix segment, you can write it like this. It's just this kind of diagram with 4 propagators like this, and with external factors sitting on the external legs, some kinematical factors. And the same kind of pattern is true up to 4 loops. So we constructed this amplitude way back 35 years ago, coming from string theory. And it was a big, I think it was a big surprise for anyone who had not been doing string theory that the result would be so simple. In string theory, closed string theory, you have only one diagram at each loop order. So, so somehow, from a string theory point of view, perhaps we were not so surprised when we got it. We probably should have been more surprised than we were at the time, because we were somehow, destroyed by our string theory, thinking that it should be like simple like that. But from a field theory point of view, this is really trying to tell us something. And I think what it's trying to tell us is that there's a lot of symmetries in these field theories. There is this saying that in quantum theory, anything can happen unless it's forbidden by a symmetry. So the more symmetry you have, the simpler the result is. The more you sort of exclude from coming in. So I, at that time, was so hung up on it, it looked just like a scalar phi-cube theory. So this is how I got into my formulation of n equals 4 as in the Lag. But I'm not going to discuss that. I'm instead going to go back to this n equals 4 and ask this question: how much symmetry can we milk out of this expression, so to speak? Because then, turning it on the other side, you would say that knowing the symmetries, that tells us something about the basics of the theory. So, this action was constructed using maximal supersymmetry in component form by Clement-Julian. That's why you would say that this paper had to have 124 pages, because they were dealing with this multiplet, which consists of one graviton, 8 spins we have, 28 vector fields, 56 spin 1/2, and 70 scalars, which is an enormous number of fields. Slightly after their paper, what Howe and myself, we formulated in a superspace formulation. And then we constructed in terms of one superfield. That was a 56, so it was sort of a spinorial field, and this 56 was an SU8 symmetry. And it was a function of 8 4-component spinners. And if you write it out, it probably has billions of components. So we could, instead of just using these 256 components, well, when Clement-Julian worked on it, of course, for the graviton they used G or H mu. For the vector fields they had what did I miss? mu. So they had also non-physical degrees of freedom in their way of doing it. Here there were lots of auxiliary fields, as we said at the time. But in a sense, this formulation was useful. So people discussing properties of n equals 8 have mainly been using either of these ones, often variants of this. So this is what people usually do. But we, in the aftermath of what we have been doing with n equals 4, we proved that it was finite, we also realized that the formalism that we were using then could be used for other supersymmetric theories. So we constructed also a formulation which I'm going to describe later with 2 of my students at the time. We studied the theory in the light cone gauge, where only the physical fields are remaining. So we could write the corresponding superfield, which no index, and it has only 256 components. So the price we have to pay then is that the Hamiltonian will be obtained as an expansion in the coupling constant. And in the beginning we constructed only the 3-point coupling. Another price we have to pay is that this formulating like this, it's going to be non-local on the light cone. But that's a non-locality which is not dangerous at all. So before showing it, let me go back a little bit to what was found in this n equals 8. So one remarkable fact about this 4-dimensional theory is that the Hamiltonian is invariant under an E7-7 symmetry. That was a big surprise. Bernard-Julian, comes from a famous family of mathematicians, so I think he had inherited his uncle's library or something, and he found some old book about exceptional groups, and that's where he found this E7. It's funny because it's a non-compact version of it even. People have been discussing exceptional symmetries in terms of grand unified theories, but then of course it's a compact version. It was even a non-compact. And the way it works for them was it worked as a sigma model for the scalars. And you can think about, there were 70 scalars. 70 is 133 minus 63. 133 is the adjunct representation of this group. 63 is the adjunct of SU8. And SU8 is the maximal symmetry. So this was somehow plausible in a sense. For the vector fields, it's a duality symmetry, and it didn't touch the other fields. And in superstring theory, it comes back as this U duality. So it exists also. So this is, there's such a symmetry. It was very mysterious, I would say. Why it was there, it's hard to know. And when you come back and hide further, so in D equals 3, the symmetry, this is what Julia at the time was saying. That must be an E8. I think it was proven by John Schwartz and E. Marcus. They constructed that theory. And also, and then Julia at the time, way back, 35 years ago, more than that, argued that in D equals 2 there should be E9 and E10. I don't think he went further than that, but if D equals 0, what is D equals 0? Well, it's sort of you look at the quantum mechanical theory with just one time. Here, and these E9, E10, 11 go outside the ordinary classification of Cartan. So these are infinite dimensional algebras. So this is an affine Kac-Moody algebra. So this is the one which is sort of best known, even though it's not known in great detail. So this observation and its argument and its ideas have been very much worked on, in Europe. So all these people, West, Nicolai, Damour, Anglais, have been working on this for years. They get all sorts of views out there. They see all sorts of signs, that these are very important symmetries somehow in constructing the theory. But they've also argued, especially Peter West, but also the other people, that these symmetries should be around also in the higher dimensional symmetries. So, for example, this, if you think about this E8, here it's connected with D equals 3. And if you, in the paper by Julia, it was sort of obvious that it was E7, there's no trace of E8. But somehow, they've been arguing that all these symmetries might be around in higher dimensions. So, the question we asked at the time, some years back, especially with Pierre Ramon and these graduate students at the time, is what happens to this exceptional symmetry in this light cone formulation, where sort of every symmetry should be a symmetry between the physical fields. If you describe the whole theory in terms of this one superfield, how can you have a symmetry that acts only on, say, the bosons of the theory? So we said that, and let me now describe how we formulated the supergravity theory in the light cone gauge, in this light cone superfield. So what we do is that we will introduce sort of a light cone formulation. We introduce the light cone coordinate. So we take x plus here to be the time. Dirac said in a very famous paper called Hamiltonian that any direction within the light cone can be sort of a time evolution parameter. And especially you can take the light cone directions. So we're going to take x plus as a time. X minus is then a space coordinate, so to speak. And we also complexify the transverse, so we have an x and x bar. So the only indices you will see are plus and minus. And similar for the derivatives. And then we introduce thetas, 8 thetas. So these are complex, but they have no spinor indices or so. And the upshot of this is that if you think about it in 4 dimensions, the spinors, and if you only have, or we're only going to have covariance in terms of the transverse space. Then the transverse symmetry is U1, and in U1 you don't really have spinor representations, you only have complex, you can have Grassmann numbers. So the only index here you see will be an SU8 index. And now we're going to construct turns out that if we look at a space like that with the x's, but instead of the x minus here, we subtract this part here. Then we can find that the representation of the supersymmetry is written in terms of a field which is just a function of the theta, no theta bars. So this is the whole field, and of course the theta bars are hidden in here. But here you can see that here you have helicity 2, helicity 3/2, 1, and then you go all the way down to minus 3/2, minus 2. So this is a superfield which contains all the 156 degrees of freedom. It satisfies certain conditions. These are some kind of chiral derivatives in this vacuum space. It satisfies these two. And also it satisfies this condition, which looks rather complicated. But it essentially tells you that if you take this field, you complex conjugate it, and you turn it inside out, then you get it back. So it's another way of saying that this guy here is the complex conjugate of that, this here is complex conjugate of that, etc. So it's a highly constrained superfield, but it contains just the physical degrees of freedom. And so in order to write a dynamical theory for this, you could either do it the hard way, and I will come back to that, to fix the gauge for all the fields, introduce the gauge conditions, and then solve for all the unfixed degrees of freedom, because they wanted to satisfy kinematic equations. But the other way is to say that this should be a representation of the n equals 8 super Poincaré algebra. And then we have to construct the representation by having generators acting on this. And we can do that by looking, we do it for the free case first, and we put this time to 0. Then we have what's called kinematic generators. So these are, in the Poincaré case, these look like the ordinary generator. They act, just on the superfield, linearly on the superfield. Don't look too much into the details, but then you'll find also that there are what we call dynamical ones. They are the ones which take you out of the quantization, which is P minus. And this is the Hamiltonian. Here you see this kind of non-locality. But they're all, it's just fun to work with this, so don't worry. And then you have these guys here. Always in the like one is the one with minus directions that are the difficult one. I'm not going to write them out. This is what in the old string theory, when you computed them, you got 26 dimensions to be the only solution. If you look at supersymmetry, we can also distinguish between the kinematical ones, these. Here they're linearly acting, and dynamical, which at this stage looks like constructive. They're more complicated. But what's happening when you turn on the interaction is that the dynamical ones, they will have higher order terms. So, for example, the Hamiltonian, of course, will have 3-point coupling, 4-point coupling, etc. So this is, this is like doing it at the Hamiltonian level, at the equations of motion. So the supersymmetry is written in this way. Yes, here the Q pluses. They only computed this E plus, which is essentially like a number. P plus, you can think. This is the spectrum generating part of our supersymmetry. These ones commute to the Hamiltonian. So this is in a sense like having taken the square root of the Hamiltonian. Sometimes one talks about that in supersymmetry. So you will see that all the U's will be in this Q minus. It will get interaction terms. And if you compute this anti-commutator, you will get the Hamiltonian. So you will get the full dynamical theory. So all dynamic generators will get interaction terms. So this is the name of the game, how to construct this kind of theory. And we can construct the Hamiltonian to first order. We can elevate it to an action. So here you see the action looks pretty simple. This is a three-point coupling. It's as simple as it can be. Yeah, don't worry, you know, the fact that in the kinematic terms there are these one of deltas is because, if you remember, I should have said it more properly. Okay. The reason why we have the superfield, we can have all the physical degrees of freedom in one superfield is that the dimensions of the thetas are compensated by this del plus. So there is this non-locality built into here, but it means that all these terms have the same dimension. So there will be one over this derivative floating around. But one over a derivative is like an integral. And in principle, there are all sorts of ways of defining it. And there are all sorts of ways of calculating with it, which is, as I said, just fun. So
there's no center extension to this.
sorry?
There's no center extension to this as
no.
you can do
Well, I mean, there could be. But we're, for this case, since we're not, but that's it. So you see, I would say that if you look, it was this dynamic supersymmetry, which is, this is the order kappa term in that. And now this Q here is what I called Q plus before. So this is just a linear operator on this. So even though there are, you know, it looks a bit complicated, it's rather simple expression. The next order is more complicated. It contains about 50 terms. But, you know, in component form, the 4-point coupling, if you write out the 4-point coupling in Clementina, there are about 5,000 terms. So this is, you know, why I'm saying that if you do the wrong thing in this kind of theories, you can end up, you know, filling every piece of paper you have or whatever, you know, the formula can be however long. So this is, and we know the next order here, certainly, but let me not write it down because that's going to screw up a lot of things. So if we now look at these E777, let me just give you the result first. And this took us months to calculate, but let me give it first to so E7 we can write as I said, E7 divided by its maximum subgroup, which is SO8 times SO8. So here you have 70 generators, and here you have 63 generators. This is a good way of parameterizing the E7, and if you want to write the commutators of the generators of E7, you write it in terms of this 70 and 63. And if you look at this nonlinear, this will be nonlinear. This is just the SU8 which I showed in the superfield. But this transformation will have 70. It will be just like a sigma model transformation. It will have a term which is 1 over kappa, and you see, this is a constant term. It's written in a slightly funny way. It's only going to affect the scalars, the 70 scalars. So these are 70 parameters. But to the next order, we can write out it looks like a rather simple expression. Here's the 70 parameters, and here these are 4 of these covariant derivatives multiplying. Here there are 3 and 1. So this is just a sigma model type of symmetry. There will be a higher order term, so this will go up to infinity. So whatever I'm saying is that I'm not doing these transformations to all orders. I'm doing it to just a certain order. which means that when I'm claiming a symmetry, I'm only claiming it to a certain order. So it's not, nothing is complete. But this is, so this is the kind of symmetry we find. But then you find, that this is transforming all the fields. So this is what is new. So, for example, the graviton, to this order, we transform it like this. Here you see helicity 2, helicity 1, 1, helicity 0, helicity 2, helicity 1/2, 3/2. So with specific coefficients. Also the spin 3/2 has a certain kind of transformation. So why is it that when we do it like this, get all the fields to transform, while in the covariant form, they don't? And then I have to, let me just sketch what is happening. So what I said is that, okay, yeah, you can, you see if I, so I'm going to sketch, because this turned out that this was, we were trying, I was confident, I thought we would be able to guess this and just check that it worked. But we were not clever enough. So we had to go back to the drawing board. Really start with supergravity, actually even in this component form. So for example, so we had to do, for the vector fields, we had to put h, say, mu, minus downstairs means plus upstairs. After 0, we have to have 4 gauge conditions like that. And then all the terms with h, so mu plus, we just solve. There would be satisfied equations with the plus up here, which is not the time derivative. It's just a space derivative. That was related to this. Yeah, it's a bit. It's conjugate to x minus upstairs, which is the space. So this, so we just we solve all these things, put it back. Similar for the spin 3/2, but we really did it for the vector fields. And you we put a minus equal to 0, and then solve for a plus. Put it back. But then we have to do another thing, because when we do all these things, we will get time derivatives, say in the 3-point coupling. And if you get time derivatives in the interaction terms, this goes back to Poincaré in 1850. There's a way of canonically, getting rid of them. But there's an easier way here. You just make a field redefinition. So what we do is that for this vector field, we introduce a new field which we call B mu, which is A mu plus things like that. And when we introduce that, when we solve this in terms of that, we push all the time derivatives up. So what's happening is that we somehow get new fields. I'm actually really looking, because these are the ones which we then also linearly combine to complex, we complexify it just to see if we have 2 of them. So by getting rid of all the time derivatives, we reshuffle all the fields, so to speak. And that's why suddenly all the fields now transform. It's a very long calculation, and in retrospect, this expression, I think, can be switched off the light. Oh wait, somehow, I mean, perhaps there is a more canonical way of deriving this kind of transformations, but in the end we gave up, you know, we really did it from scratch. But anyhow, so we have, now we knew that this is a symmetry. There is, and we can check that it's actually a Hamiltonian. So this quotient space commute with the supersymmetry. And this is funny because even though, of course, SU8 do not commute because they are transformed as 8 under SU8. So how can this be, you might say? And when we were doing it, we suddenly realized that it sounds like a paradox. Because the point is that if you do 2 east, you don't need this guy, I can write this T, I, J, K, L. I commute 2 of them, M, N, O, P. That turns out to be epsilon I, J, K, L, M, N, let me say, O, R, T, P, R, which is, this is the SU8. And this is E7 over SU8. So 2 of them, so they really talk to each other, you know. So how can it be that we can demand, because suppose you do Jacobians with is this, and well, 2 of those and 1 cube, for example. Well, it does work because of the nonlinearity. But I mean, we're very nervous. Then I described this to Ed Whitton, and I came here, and he said, no, that cannot be true. And then he said, because of the Jacobians. And I said, if you really do it, it does work. Okay, I said, I knew you were hiding something from me. But anyhow, it does work. It means, you know, that this 7 here commutes with Q, which means that it commutes with the Hamiltonian. So then, you know, so this is a symmetry of the Hamiltonian. So this non-linear part of the exceptional group is also a symmetry of the Hamiltonian. Like, you know, supersymmetry. So note that this exceptional algebra and the maximal supersymmetry, they stand on the same multiplet of the superfield. And both are non-linearly realized. So the 70 of this is non-linearly realized. The dynamical part, the dynamical part of supersymmetry is also non-linearly realized. So we can use both to find the Hamiltonian. So which is the chicken and which is the egg? Which is more important, the exceptional or the maximal supersymmetry? This is the question. So, in a sense, you would say that both are, you can use either of them. Of course, in the original construction, they used maximal supersymmetry. But in principle, they could have used that too. And you will see that, you know, they are somehow, I shouldn't say on a dual, but they're very similar, and they work, you know, I think it's remarkable that these exceptional algebras can be spanned on the same multiplet. I mean, it has to be spanned non-linearly, but even so. So let's now look at 11 dimensions. So what we would like to do is that we will use this superfield, but now we say that we also augment the space-time with 7 more coordinates. Now the transverse symmetry will be SO9. We will write it in this bit cumbersome form. Because, you know, the thetas that we're at 8 thetas. We like them to be spinors now. But they cannot be spinors under SO9, so they have to be spinors under SO7. So this is going to be linearly realized, covariantly realized, so to speak. This is the old transverse, which is just the helicity operator. And this is alternate. So we have, these are new generators of the Poincaré algebra. This is the rotations in SO7. This with just one index means that there is a rotation between the new coordinates and the old ones, so to speak. The ones for the transverse we didn't use any index, we used x and x bar. That's why we have to, these are complexified, so to speak. So all these are linearly realized. So we have to construct those generators in order to have an 11-dimensional field. But what we are doing is that we use the same superfield. So we are going to write the Poincaré algebra in 11 dimensions in a funny way, in a sense, because we divide it up into pieces. So can we then, and what we need to construct is this dynamic of supersymmetry in 11 dimensions. And it's linear in derivatives. So this is the old derivatives that we're using. These are going to be the new one. In the 4-dimensional case, we did not use this derivative. And I'm sure. So it should be linear. So this is just the same as in 4 dimensions. But we have to construct new terms. So this is the new kind of derivative into the new, you know, these 4 to 10 directions. There are certainly these dimensions. How about this guy? Well, these two terms do not exist in the equals 4, but in the equals 11 case, because there's no room for them. But now we have a smaller R symmetry, namely SO7. And for if we had written the D equals 4 theory with an SO7 R symmetry, then we could have had such terms. So it turned out, you know, if you go from 11 dimensions to 4 dimensions, like Clement and Julia did, you have to do all sorts of, you know, duality transformations in 4 dimensions to get it into the most symmetric form. So we have to, so the name of the game is now to try to find expressions with all these derivatives and see if it can work. So I said, don't look so much into the details, but the terms with this kind of derivative was like that. We can write it in a form which looks like more like this, where we introduce this kind of operator, and we just take it to linear order. This is like some coherent state. In a sense, it does. This is a very nice form of using it because it's very easy to commute this with to check the Lorentz properties of these things. So we are sure to get the correct commutations with all the kinetic generators. So now we have to just check these new ones we had. So of course this will, when I commute that, it will create new term. So for example, the crucial commutator that we have to check is this guy. This is one of the new, which is taking you from direction 1 to 2 to 4 to 10. And it makes, I mean, it takes one of these supersymmetry generators to the complex commutator. So what we have to do is that we just have to try to write the most general form and then do this commutator and see. And you know, after a very long calculation, we find a unique result. So this is the original term. Here we have to write something, and when we solve that, we have to do it to the 3rd order. So that's a lot of terms, but we can write these terms in a nice way, you know. So two of them. And this term, the new term with this kind of derivative, we have in principle to expand to fifth order if we want to. But we can do all the calculation in this. So it simplifies things enormously. So this is the result. This is the supersymmetry transformation in 11 dimensions, working on the superfield. It gives you the right algebra so to that order. So we have constructed the 11-dimensional theory in terms of the superfield. I mean, it's a roundabout way. It's not. Here we're essentially interested in constructing it and looking at its properties, not looking at the details so much. So, in principle, we can compute the Hamiltonian. And you know, since we know that there is a unique solution, we have solved the problem now. We don't need to do any more of the algebra. The question is, would this be invariant under this E7 transformation? No, not in the form we have it. It's not invariant under these E7 transformations that we have computed. It doesn't work in 11 dimensions. You say? However, then the question we can ask, because this was a very special way of lifting the theory from 4 to 11 dimensions. We were lifting it just to keep the supersymmetry, so to speak. Can we lift it some other way? The answer is yes. So another way is that we don't bother about supersymmetry. We only bother about Poincaré invariance, because that's the only thing we need really to have Poincaré invariance. So we construct a new kind of derivative here, where you see this is the one that we had before. These are the new ones. And we try Hamiltonian. We just take the old Hamiltonian and we put in this new derivative here, so to speak. And we ask, is this Poincaré invariant? Well, when we check the Poincaré, we did this parameter we had, turns out to be 1. And then it turns out that if we can interpret this, we can perform E7 transformations on this, and it works. So we have to. It's very tricky about since we're now the superfield we're now the theta we don't. We say that this just transforms under its rate again. So the Hamiltonian we have constructed is different from the previous one. In this case, it's E7 invariant. But it must be the same theory. There's a unique theory in the dimension. So what we find is that there must be a field redefinition taking it from one formulation to the other. So when you take the theory from 4 dimensions to 11 dimensions, we find that doing it one way, it's supersymmetry. Doing it another way, it's E7 invariant. So in that sense, E7 is still a good symmetry to define the theory. And as people have sort of conjectured, it is, we can construct, at least to this order, an 11-dimensional theory which is E7 invariant. So it's not tied to use it just in 4 dimensions. We can also go further, now getting even more complicated. To look at D equals 3. In D equals 3, we're supposed to have an E8 invariance. The maximal subgroup there is SO16. And so you write E8 in this as 128 non-linearly realized and 120 linearly realized. And we also showed so we will use the same superfield. We have 128 scalars, 128 fermions. So now you see that SO16 it's the largest R symmetry one can have on this superspace. And all the scalars will participate in the sigma model. And one can construct, again, you know, these transformations on the super. Don't look at, you see, it looks, well, it's very complicatedly written. Just say that the supermultiplet can also be used to represent this EA. So we use the same superfield in 3 dimensions, and then we can find that it's EA invariant. So, can we obtain this formulation by just dimensional reduction from D equals 4? Well, then it turns out, you know, in D equals 4 we had a 3-point function. But if we should have an E8 invariance, which means that we have an SO16 linearly realized symmetry. In SO16, the 128 that we have is a spinor representation of SO16. We cannot have 3 spinors, which means that in an E8 formulation, there cannot be a 3-point coupling. So what you have to do is that you have to do a field-relay definition to get rid of the 3-point coupling, and then one can obtain the. So what we could have taken the 4-dimensional theory down to 3 dimensions, do field-relay definitions, and find that it's E8 invariant. When people do that covariantly, they have to do duality transformations. But there is no duality transformation in the Lycon formulation, it's just field-relay definitions. So we can do it. So then we can ask the question, can we now go back up? If we will go from 3 to 4, then one way is to break this SO6 into SO8 and get the old formalism. But we should also, you know, so this is like what I did before, to keep the supersymmetry. But we can also try to keep the E8, and then we have to keep this derivative structure. And there should also be a way. So now I'm claiming, both should be the same thing. So I'm claiming that there is a formulation of n equals 8 supergravity in 4 dimensions, which should have an E8 symmetry. And that's sort of hidden. But you see this, you know, there are, you know, Byrne, Dixon, and these people have been working on really trying to do these calculations in n equals 8 supergravity. And they've been shaping up to the for-loop order that it's finite. But they also find that it's better than these arguments that people have, counter-term arguments that people have been arguing from the kind of superfield that I was decided the covariant superfield. So my claim then is that, well, the theory is better because better behaved than what meets the eye, what you can do by you know, sort of counter-term arguments, because there are hidden symmetries. In this case, a hidden E8 symmetry.
You say the same logic can be carried out from D to 0 up to the both field points, say hidden E10, E11.
Yeah, I've not said anything about E8 and A9, E10, but you know,
If I believe those conjectures, then that will be.
Yes, if one believes those conjectures.
Yeah.
So that's why, and of course, Peter West is claiming that there's an E11 symmetry in 11 dimensions. So, so I was I was at UCLA during this talk, and I was talking to Stephen Byrne, and I think he got a bit excited because, you know, if it's a hidden EA, that means that there is the subgroup, the linearly realized is SO16. So there should be an SO16 invariance underlying the amplitude. And that would probably cut down further the number of possible counterterms. So what I'm claiming is that we could expect better quantum behavior than what standard counterterm argument would give. So, what does it say about quantum finiteness? We don't know. I mean, I think this is a very bothering aspect. When Palau and I had constructed a super space formulation way back in 1979 or something, Palau and Flintstone, they used that to construct some counter term. And they were arguing that there should be a 7-loop, at least a 7-loop counter term possible in any position supergravity. And people have been speaking of that. And you know, that it's impossible to compute the 7-loop. Even this 4-loop amplitude that Vernon constructed would be the same as solving 10 to the 26 Feynman diagrams. More than brain cells, or more Feynman diagrams than your brain cells. So that's a good question. Can the brain solve something with more degrees of freedom than but even so, and I think they are on the verge of finding the 5-loop. They've been saying that. They said, well, I was saying November, beginning of November. Björn is an optimist, but what they're doing is remarkable. But would we ever be able to say, because then people, they come with the 5-loop. Oh, but we said it should be infinite in 7-loop, which is not very fair in a way. But what they can do is that they can also check it in high dimensions in a bit, you know. So they will have some, I think they can still argue that the result is better than what counter-term arguments based on, you know, some covariant superfield is doing. So from that point of view, they can indicate that it's better, but in order to prove it, probably need some proof to all orders, and that's very difficult. So, as I said, only explicit calculation can give different answers. And it's bothering because it would be so nice in a sense to say that any coset supergravity is infinite, because then we can forget about it in a sense, you know, it's not going to, there are a group or a class of people who don't like strings so much that they would say that, you know, if any coset supergravity is finite perturbative, that's good enough, then we can use that, you know, as a fundamental theory. I don't subscribe to that because we know that, you know, that any coset is a low energy limit of the superstring. And the superstring is dual to n equals 4 Young Mills. When n equals 4, you know, you can go this way, n equals 4 gives you, the superstring gives you the n equals 8. So why should this doesn't play a special, n equals 4 does, because SU8 perturbative is like n equals 4 like n equals 4. That's the way they do the calculation. Anyhow, we would have liked to know this 30 years ago, you know, then we would have left this problem. But as you say, is this the tip of the iceberg? E9, E10, 11. So I don't know. I mean, it's intriguing. I would like to somehow get the handle, see if I can get there. If I can, in this formalism, get the way of, especially doing E10, which is somehow the most, this algebra is the one which is most known about. So the question is, does this have consequences for the string? Possibly, and that's another idea one can get. Of course, we have constructed the string based on supersymmetry. And so we have failed to do M theory, extending it to M theory, because we're insisting on the thinking is in terms of supersymmetric theories. Perhaps if we can get rid of that, perhaps you can even, you know, use these exceptional symmetries instead to define M theory. Can we it's too difficult for me, but I mean, it at least gives some hope. So, you know, I think there is something, what I want to convey to us is something very deep in these theories, and we still don't know, and we need to know it, because we need to understand all this picture between n equals 4 Young-Mills, superstring, and n equals 8 supergravity. And in the meantime, we have to sort of try to work out as much as we know about the various parts in this triangle. And this is one little piece of information that it is exceptional. We should take these exceptional groups really seriously. Okay, I think I should stop there. Oh, this is my grandchildren.
Taking some thoughts.
Sorry.
Nobel Prize.
No, they're runners. Okay.
Okay. Yeah. Thank you.
I'd like to ask about I mean, if I come from supersymmetry, and there's a unique theory in 4 dimensions, A supersymmetry, that's supergravity. Okay. Are you saying that if I start from global symmetry, E8, then I can also somehow use a symmetry and find a unique theory that would be the supergravity?
Yeah, what I'm claiming is that there ought to be a way of writing a 4-dimensional theory with an E8 invariance, where you don't use supersymmetry. I mean, somehow supersymmetry is there, but it would be very difficult in that formulation to see it. And that would be an alternative way of doing it. I don't know exactly how to do it. But as you saw, actually when we wrote this, when we went from 4 to 11 dimensions, keeping the 7, that kind of action looks simpler in a sense than the one which is supersymmetric. We don't know what happens at the next order, the 4-point coupling. That might be very difficult. So Peter West believes that, you know, going further up, one has to introduce more fields in order to really keep the symmetry at each order. But I think that these symmetries are there, and I think one really has to understand the exceptional symmetries later. I think it's remarkable that you stand them, although non-linearly on the same kind of multiplet as symmetry. So it is as if supersymmetry knows about exceptional groups and exceptional groups about supersymmetry. So there's some deep mathematics here.
So sounds like a very good topic. Just to construct general nonlinear symmetry model for exceptional symmetry group, not necessarily E8, but
yeah. Yes. Yes.
So the E7, E9, the act-on scalars, these are reflected physically on the S matrix, where you have these double soft theorems for the scalar, which reflects the E7 and the E7 in 4 dimensions and the E8 in 3 dimensions.
Mm-hmm.
So if there's a proposed E8, so the question is, do you expect the E8 to act on scalars? I mean, there's different ways of formulating things, but always assume if symmetry is relevant for the
So the E8, you know, in that sense, has to act on all the bosons in 4 dimensions in some way.
So then why would we expect to find some soft theorems which are not explained by the original E7, if that is true?
Yeah, the relating different boson fields.
Yeah,
that's a nice way, yeah. But you see, going back to when I was starting, when I was saying, look at You know, in this one loop expression here, if you really look at the expression for that, then you see that it treats all the bosons in a similar way. So I would claim that if I had been smart, I would have probably been able to argue that way back that this indicates that there's an SO16 invariance in this, because the SO16 is linearly realized. So that would just relate the bosons here. But all the bosons are treated exactly the same. I mean, there are some of these kinematical factors here, but that just reflects the spin somehow. So, so I think then, you know, if you say the E8 corresponding, that would be more difficult. Actually, the problem is that it's non-linear also. So you cannot, yeah, that makes it slightly more difficult because you probably have to relate 4-point functions to 5-point functions.
Yeah, that's what the software is.
Yeah. No, exactly, yeah. And you have to, which means that you really have to be able to compute this higher, yeah. But it is, yeah, that's a very interesting thing to say. So I claim that I think it's too difficult to compute it, so I can safely say that I believe that it's there.
Can I ask a historic question?
Yes.
So in the paper that you had to write this one loop amplitude string theory, I noticed that in the formula you actually had the one loop answer, but you didn't write it as a phi cube box. I mean, it's essentially a Feynman parameterization representation. So, so I was wondering if it was a phi cube box, you would have wrote it in the paper. So I was wondering, did you know that you had a phi cube box, or?
Perhaps not when we wrote the paper, but somehow.
I see. Yeah, because you only had the Feynman parameterization, and that naturally came from the string theory.
Oh yeah, no, okay. Because we were mainly interested in sort of the finiteness properties of the amplitudes at the time to see, you know, So that probably came. Yeah, thank you. I haven't looked at the paper. Yes.
I'm a bit confused. This n equal to 8 supergravity, is it finite? Because you were mentioning counter terms. Does it
No, this is what I said in the end. I don't know if it's finite. You know, people have computed it up to 4 loop.
Oh,
and found it finite.
only worries are beyond 4 loop, maybe.
And they are trying to do 5 loop. And the arguments that people have had, based on counter arguments, is that it should be infinite at 7 loops. But you know, 7 loops would take all the computers in the world, you know, and other planets in.
But is it impossible to prove this finiteness by induction or things like that?
I don't know. I mean, nothing is impossible. No, someday. I mean, if people still would be interested in this, you know, one day people will find an analytic proof, if it exists, or analytic proof that it's infinite. But this is what I said at the end, you know, it's a bit annoying that we cannot settle this issue, because this is, I mean, it's very hypothetical. I mean, this is a theory which is, it's not very physical in a sense, you know, so you cannot go to the research council to say that if you solve this, we will have solved it. So this is an esoteric problem, but I believe it's very important for the general field of string theory, but exactly the importance of this, we don't know.
How do you think this would make an impact on fundamental string theory?
So what?
I mean, this is about supergravity.
Yes.
And how does it connect with our supergravity?
Well,
this would lead to string, it's a string or just effective symmetry, effective field.
you know, this is a division between Europe and the United States, because if you go to the United States and talk about this, only people like C. Berners are interested, because they're interested partly because they're good at doing these kind of calculations, and also you get might be, but you go to Princeton, nobody will care about this.
But they don't think it's live up to the strain and then.
No, I mean, we strongly believe that the superstring theory should be finite.
Yeah.
And those proofs, I mean, we believe it. So, no, it doesn't affect string
I mean
theory.
the E8.
Yeah, the E8. Well, also, so we were at the Institute in Princeton, Ramon and I, during part of this calculation, so we were discussing with them, and he was friendly, but said, oh, he said, E7 is just a duality.
You have effective.
No, he did.
In answer to what effective.
Yeah, I don't think he found it very interesting. So doing it this way, it's not a duality. So it's more like a nonlinear sigma model, because there were always these two sides to it. It was a nonlinear sigma model for the scalars, and it was a duality symmetry for the vector fields. But duality, as I said, symmetry in the Lycon, when you have eliminated all fields, it's just field definitions. So here, the important thing is the nonlinear sigma model in aspect of that.
Actually, on that comment, I have a question. So in usual duality symmetry, you need to invert the coupling constant for the electromagnetic duality.
Okay, yes.
And under the dualing, you need to reflect, exchange the coupling.
Yes.
So how does it reflect? I know how nonlinear symmetry reflects on the scalars, but I don't know how it reflects on the vector. Translating this as a transformation on the vectors, how do you see that you actually also need to invert the coupling constant for the electromagnetic dual?
I don't see that. When in order to the way to it's not so much. You see what's happening in it's more like that. So we have 28 of those. And what one has to look at some F U, 28 of those, and then there are some, and you have to look at the dual part of that, and you define. This is very sketchy. So you find something like that. So that is a 56. And this is what transforms under E77 linearly. So this is the lowest lying representation of E7. So it's more like that you use the field that it's dual field in order to construct a representation of E7. So that's how one can see it on the vector fields. It's very roundabout. So that's why I think it's much more important on the scalar fields.
Yeah.
Okay. You can ask other questions as well. Because he is also a member of the committee, the Nobel Prize, Nobel Prize. Okay, so if no other question, we next thanks. Yeah.
之前我在看新的
就说你说到底说那个差别很大的。
对什么条件结束。
Yeah,
Non so se riesci qui non seminato che la NPH.
yeah.
Everybody prepared? Laurent? Not here before.
Do you want to ask me more questions about in the interview or?
Yeah, maybe. So, ask you about your vision about the future.
Oh, I see.
How do you advise a student now? You could advise them to do something easy or do something I mean, because we come from also from the Nobel Prize.
Well, I mean, this is far from Nobel Prizes so far, you know,
Yeah.
because it's a problem in theoretical physics that all these issues. Yeah, let's go. But you said she was in the library, you said, so.
Yeah.
没有，不是那一段，因为蔬菜打到那段路上回来，开车那个到那个什么省道那次。对。你要待着。先放掉肉过来，全走。我真的没听。